Hello and welcome to this ALINT-PRO tutorial. My name is Brandon, and today I'll be showing you some more library functions as well as the clock generator to help facilitate your block level constraints and improve your overall linting results. I'll get right into this one by showing once again the list of library functions within our command reference guide. In my previous demonstration, I showed the lib asynchronous FIFO command, so now I'll take some time to show off some of these other commands, starting with those related to constraining logic gates. These constraints can be used in gated clock instances where logic is unimplemented. For example, in the project I have open now, you can see I have a single violation involving AND gating of clocks, and this is because the tool right now recognizes the structure relevant to this rule, which we can see via the rule description viewer. Comparing both diagrams, we can see that this component here is acting as the AND gate, despite it having no actual implementation yet. And this is because we've provided the constraints for that block. Looking at our other module here, we can see it is recognized as a black box only, and therefore throws this violation here as the tool expects an OR gate for this particular layout. So let's go ahead and add that constraint. Within this file, you can see all the constraints I've already provided for this project, including the use of this libdff function, which was used for those flip-flops in the schematic. Looking at our logic gate constraints, however, we can see how to properly write out one of these commands. For this type of constraint, we use the setPin command with this function argument. The argument is provided the lib and function, which simply takes the inputs of the logic gate. Finally, we then provide the output pin for the logic gate as shown. Right now, only this AND gate is constrained, which we saw in the schematic. So let's go ahead and uncomment the constraints for our OR gate here and see how it affects our violation. And as we can see with the constraints provided, the tool now properly recognizes the unimplemented logic as the necessary OR gate, and the rule is no longer violated. Let's now move on to another example involving constraints for something a bit more complicated. In this project, we can see a black box which represents a currently unimplemented RAM module. Just like in the case of our previous constraints example, we can tell the tool how this black box is to be recognized even if our source HDL is not available. And this will be done by another library function. Going to this project's constraint file, we can see a single constraint for a buffer, which resulted in those two buffers before our input. It is described similarly to those logic gates we just saw, as it utilized the setPin function. However, library functions can be used with our setCell commands as well, as we can see in this particular constraint. Because we're trying to describe a RAM module, we are passing the libram function to our function argument. This particular function takes memory interfaces as input, which are described via another library function, the libInterface function. Each interface has arguments for pins expected to be found on memory, such as input, address, clocks, and others. And by providing this function twice, I can even describe a dual-port memory device. Additionally, these interface functions are quite configurable, allowing asynchronous or synchronous controls or optional read enables. And for a list of these options, you can once again refer to the command reference guide shown earlier. So with the constraint now uncommented, let's now rerun the project and see our resulting schematic. The tool no longer recognizes our unimplemented module as a black box, and now properly displays the module with correct clocks, inputs, and asynchronous clear here on the side. Moving on to our next example, I'll now show a library function that can be used on a more general type of logic, as this project utilizes the libsynchronizer function. If you have your own custom synchronizing module that doesn't fit within the constraints of other functions, then this is the constraint to use. As we can see, I've already provided constraints to this module, as it is not displayed as a black box. However, we still have a few violations here relating to synchronizing data as well as incorrect use of custom synchronizers. And this is because the tool recognizes the clock domains of the custom synchronizer and sees that our read clock is connected to our source domain, which would certainly cause errors down the road. By providing the correct clocks to our custom synchronizer, that is the clock of the destination domain, we can now see that our design is compliant with those previously violated rules. And with that, that'll mark the end of our library function examples. Of course, more library functions do exist to cover other types of modules, which can all be found within the command reference guide. But I'd like to now go over one more example to wrap up some more on block level constraints. In this project, I'll be utilizing a clock generator fed into some FPGA clock multiplexing cells. This time, my constraints are being applied to the clock generator, a module that once again currently has no implemented logic yet. We can still analyze such a design using these create generated cell clock commands. Each command describes one of our output clocks and is modified from the master clock using some special arguments. In this particular generator, we can see a combinational clock, which simply passes the master clock, these two multiply and divide clocks, which perform the relevant operations on each, and finally this inverted clock, which will of course provide the inversion of the master clock. In fact, under our synthesis report, we can see under our clock signal that the tool has automatically detected the proper frequencies and phase shifts of each clock without me having to give any explicit constraints. And this is because the tool recognizes the master clock's name of 100 MHz and properly applied all those operations detailed within our constraints to form the output clocks. There's our pass-through, our doubled, our halved, and our inverted clocks. Looking deeper into our report here, we can see that within our clocked elements, each instance is being clocked by multiple signals as a result of those multiplexing cells shown earlier. We can see the same story within our input port analysis as well. This is because the tool is pessimistic by default and will consider both clock sources to be propagated from our FPGA multiplexers, thus grouping them into a mux domain, which can create noisy CDC output or even miss important CDC paths in some cases. Of course, actual implementation will only have one of these sources selected at any given time, and we must therefore explicitly state which one we'd wish to observe by providing a signal to the module's control pins. Fortunately, this can be accomplished with constraints if the signal is not already connected to a constant net. In the second part of this example, I've applied an explicit value to our selector signal via the set case analysis constraint, which ends up disabling those non-selected netlists and destroying our muxed clock domain. And this is accomplished because the built-in constraints for FPGA vendor primitives can see that case we just set and will therefore propagate the relevant signals accordingly. In fact, looking at our new synthesis report, we can now see only those selected clocks controlling their relevant instances. Overall, the create generated cell clock commands here were able to provide the relevant information on our clock generator module despite logic having been unavailable to the tool. Even so, we were able to recognize the proper clocking behavior within our synthesis report, and with the help of our case analysis, clean up the report for a more organized and safer analysis. That'll be it for this tutorial on library functions and other constraints. And of course, thanks for watching.